Hi everyone, in this video we're going to be continuing talking about matrices and we're going to talk about the operations you can do on them. Okay, so we know a lot about matrices already, so some of this might seem familiar. And so if A is your matrix, size m by n, remember m is the rows, n is the columns, then the scalar entry in each space, so in the ith row and the jth column, is denoted A sub ij, excuse me. And it's called the ij entry. Okay, so this is just a notation for us to have a way to represent each value in our matrix. So the ij entry, let's put some numbers there. We can say the 1, 1 entry is going to be whatever number's here in the top left corner. Let's say your matrix was size 3 by 3, then the 3, 3 entry would be in the bottom right corner. Third row, third column. Okay, so it's just our way of denoting where the location is of that entry. And then each column is a list of real numbers, which we were calling a vector. And so every column is a vector. And if we have m rows, then our vectors exist in space Rm. So for example, if we had 3 rows, then each vector would have 3 entries. And so each vector would exist in R3, or 3-dimensional space. Okay, now the columns, your vectors, are just denoted A sub 1, A sub 2, and so on, all the way to the last column. And then the number A sub ij is, like we just said, the ith entry, and this is from the top, so you always count 1 at the top, and then you count your rows down. And then the jth column, starting from the left and going right. The diagonal entries in your matrix are always going to have the subscripts that are the same numbers. So for example, your top left corner is A sub 1, 1, then the next diagonal in row 2 and column 2 would be A sub 2, 2, and so on. So anytime your subscripts are the same number, 1, 1, 2, 2, 3, 3, so on, know that those exist in the diagonals. And they form what's called the main diagonal of your matrix. Now a diagonal matrix, by definition, is a square matrix, so it's the same rows as it is columns. And this is a diagonal matrix if everything that's not a diagonal entry is 0. So the main diagonals have numbers. It could be any numbers. And if every other number that's not a diagonal is a 0, that's when we call it a diagonal matrix. And so for example, the identity matrix is a very specific diagonal matrix. This is the one where we have 1s in the diagonals and 0s everywhere else. All right, and then a matrix who has all entries of 0, we still call it a matrix. It's just called a 0 matrix. Now, 2 matrices are considered equal if they have the same size, so same number of rows and columns, and if their corresponding columns are equal, which amounts to saying that their corresponding entries are equal. So basically, if they look the same, we call them equal. Same entries in the same locations. And then if we want to talk about adding these, if A and B are both the same size matrix, then you can add them, and the result is that same size matrix whose columns are the sums of the columns of the 2 that you added. Okay, so when you're adding matrices, they have to be the same size to begin with, and then the resulting matrix is going to be the same size as well. And so since vector addition of the columns is done by entries, so you add up each entry, then each entry in A plus B is the sum of the corresponding entries in A and B. All right, and again, they have to be the same size matrix to begin with. So for example, let's try to add these matrices, A plus B, and then we'll try to add A plus C. All right, so just looking, can you tell which one's going to be a problem? A plus C is going to be a problem because they're not the same size. But A and B are. They're both 2 rows by 3 columns. So they're both 2 by 3s. So when we add A plus B, the result is going to be another 2 by 3. Okay, and so notice what we get. We just added up the entries. So if you go back real quick, let's see, we'll just take 2 of them. 5 here and 9 in the bottom right corner. So 5 came from adding 4 plus 1. Bottom right corner, we got 9 from adding 2 plus 7. You just add up all the corresponding entries. And then A and C cannot be added because they're different size matrices. All right, now, if R is a scalar, so just think of it as some number, and A is your matrix, then we call it a scalar multiple when we multiply the matrix by that number. And basically all you do is you times every column by the number R, and then therefore you kind of think of it as distribution, and you basically just multiply each entry by the number R, whatever R happens to be. All right, and so now we have a theorem with a few parts to it. So we're going to just say in general, A, B, and C are matrices of the same size, and then R and S are going to represent our scalars. So our theorem is just letting us know what we can do with our matrices and what operations are preserved. This one, when we add matrices, the order doesn't matter. Okay, so you can add them in either order as long as they're the same size matrix. And then B, this is associativity. We can add the first two matrices and then add the result to the next matrix. Same thing if we add the second two and then add the result to the first matrix. So this is associativity. We can do that with matrices. If you add a zero matrix to a matrix, hopefully this one's intuitive, the result is the original matrix. If you multiply, letter D, your sum of your matrices times a scalar, it's the same answer, same result, as if you were to distribute this scalar. If you were to say your scalar times A, your scalar times B, add the results. Very much similar is part E. And then part F, if you multiply your matrix by some scalar, and then take that result and multiply it by a scalar again, it's the same as just timesing those two scalars and then multiplying that by your matrix. So these are just operations that you can do on your matrices. Now each quantity in this theorem is verified by showing that the matrix on the left side has the same size as the matrix on the right side, and that corresponding columns are equal. All right, now let's talk about multiplying. So matrix multiplication. So when a matrix B multiplies a vector X, it transforms X into the vector B times X. Now, if this vector is then multiplied in turn by a matrix A, the resulting vector is the same B times X, but then multiplied by A. All right, so intuitively, hopefully it's going to make sense as soon as you try it. Don't get too caught up on the wording here, but just take a look. It's just two steps for multiplication. You're going to take your vector X, times it by B, then you're going to take that result, times it by A, and that's your answer. So that means that A times B times X is produced from X by, we call this a composition of mapping the linear transformations. So composition because we're composing a result, A times BX, from originally X, introducing B, and then A. And so our goal with this is actually to be able to represent our multiplication or mapping in a single matrix. And so what we can actually do, instead of saying B times X and then times A, we can actually do A times B, multiply our two matrices, and times those by X. Okay, so it's sort of like jumping from X, timesing it by A times B, and getting our result. And so if A is size n by n, B is size n by p, and X is in Rp. Now, real quick before I keep going, let me make sure you remember this. To multiply matrices, the columns of the first matrix have to be matching in terms of entries to the rows in the second matrix. So notice that these match. The columns of A match the rows of B, so that we can go ahead and do this multiplication. And then also, quick reminder, when you do this, the resulting size of your multiplied matrix, the resulting one, will be this size. It will be size M by P. So this is kind of a nice way to check if you're on track with your multiplication, like if you didn't forget any terms or get mixed up. So yes, we can multiply these because it's M columns by n rows, and the result will be size M times P. And then remember, X exists in Rp because it's letting us know that there's P entries in the vector X, and that matches the columns right here of B. Okay, So with that in mind, denote the columns of B just by your vectors B1, B2, and so on, all the way to BP, and then the entries of X, X1, X2, all the way to XP. And so B times X is just X1 times B1, or the first entry in X times the first column or vector of B, and then the second entry of X times the second column of B, and so on. And then we've seen this before, by the linearity of multiplication of A, we can just say each of those results times A, which just becomes X1, entry 1 of X, times a matrix A, times vector 1 of B, B1, and so on. And so this is just a linear combination of the vectors A times B1, A times B2, and so on, using the entries in X as the weights. So we were first learning about linear combinations, so hopefully this kind of reminds you of that. And so in matrix notation, the way we write this linear combination is the following. So these are equivalent. This linear combination here is equivalent to this matrix notation here, where we have this matrix, which has entries A times B1, A times B2, and so on. All that times X. So these are saying the same thing. X represents the weights on each of these terms, if we were to write it out with plus signs. Okay, and so thus, multiplication by this matrix transforms X into A times B times X. All right, we'll do an example to put this all together for you. And so definition real quick, if A is size m by n, B is size n times p, and we have our columns of B, B1, B2, and so on, then when we multiply, so that we're defining the product here, when we multiply A times B, the result, like I told you a little bit ago, is going to be size m times p, because the result is the number of rows from the first column and the number of number of rows from the first matrix and the number of columns of the second matrix. And the entries of this matrix, or the columns of this matrix, I should say, are just what we had up here, A times B1, and so on. Okay, so then we're just basically getting to where we can say A times B is exactly what we just talked about. So this is letting us know that equivalently what we were trying to show, this whole composition, can just be done by saying A times B, and then making that result multiplied by X. All right, so multiplication of matrices corresponds to composition of linear transformations. So it's sort of like a proof, not quite, but just sort of explaining why we can say that this A times quantity Bx is the same as AB times X. So let's work this out. We're going to compute A times B, and then here's A and here's B. So before we do the multiplication, let's just verify some things and make sure we know what size result we're looking for. Okay, so matrix A is size 2 by 2, 2 rows times 2 columns. Matrix B is 2 by 3, and so yes, we can go ahead and do the multiplication because these numbers match, and the result is going to be a 2 by 3. So when we're done, we should just make sure, okay, our answer was a 2 by 3 matrix. All right, so the way we're going to do this is we're going to break it into steps. We're going to write B as just a columns containing B1, B2, B3, and we're going to break those down and multiply each one by A. So notice what we have, 3 multiplications we have to do, A times B1, A times B2, and A times B3. And so let's verify what size each of these 3 results will be, just so you know, because these are going to go into our columns of our answer, which is A times B, but we're breaking them into steps. So I just want you to be aware really quick. Okay, so a 2 by 2 times a 2 by 1. And so what I'm trying to let you know is that each of these, when we multiply A times B1 and so on, it's going to give us a 2 by 1, which is just going to be each column of our answer matrix. So by breaking this down, A times B1 is going to give us one of the columns of our matrix AB. All right, so let's take a look at each of these products. So what you do is, and let's just focus on A times B1, is you take the row 1 from your first matrix and you times it by the column 1 of your second matrix. So this is pretty straightforward for our example because we only have one column in our second matrix, but I just want you to be aware because in the future, if these get bigger, then you need to be aware of how this works. So right now, it's just going to be row 1 times column 1, and that's going to go in row 1, column 1 of the answer, and then row 2 times column 1, and that's going to go in row 2, column 1 of the answer. And so remember how this works. We've seen this before, but let me break it down for you. So let's see how we got 11 and negative 1. So row 1 times column 1. What you do is you say each entry, so the first entry in row 1 is a 2, and then the first entry in column 1 is a 4, so you multiply those. So you say 2 times 4, and then you always add. So plus the second entry in row 1 is a 3, and the second entry in column 1 is a 1. So you say second entries get multiplied as well. And then if there was more, you would say third entry of row 1 times third entry of column 1, and so on. And so 8 plus 3, that's where 11 came from. Okay, so let's check and do it again real quick. See if you can understand how to get the negative 1 here. Okay, so we take row 2 times column 1, and we're going to say entry 1 of row 2 times entry 1 of column 1 plus entry 2 of row 2 times entry 2 of column 1. And so 4 plus negative 5, there's the negative 1. All right, and if you want to check your work, you want to pause it and try it. For a times b2, you'll get 0, 13, and then a times b3, you'll get 21 and negative 9. And notice that all of these results are size 2 by 1, like we had said they should be. And so the answer here is the matrix AB, where each of these products, which give us a 2 by 1 vector, is going to be the columns of that matrix. And so we just have a times b1 is column 1, a times b2 is column 2, a times b3 is column 3. And do notice the size of this. It is a 2 by 3 like we expected it to be. So this is how you do matrix multiplication, a times b. Okay, so each column of A, B is just a linear combination of the columns of A using weights from the corresponding column of B. And so here's our rule for row column computing of AB. This is exactly what we just did, but here it is as a rule in general. And so if a product AB is defined, then the entry in row I and column J, let's put some numbers on here. Let's say we're looking at like the first spot, so row 1, column 1. Then that entry is found by doing the sum, so you're adding the products of the corresponding entries from row 1 of A and column 1 of B. So I'm just using an example where I and J are 1. So in general, this is how you get each entry of your product. And so the IJ entry of the product is just the first entry of that row from the first matrix times the first entry from the column of the second matrix. And then you keep doing this. All right, so we did it in our example, but take a look. So if we look at row 1 of our first matrix and we times it by column 3 of our second matrix, look at where the result is going to be at. It's going to be an entry 1, 3, that location, row 1, column 3 location. Okay, so down here, if we take row 2 from our first matrix and multiply it by column 2 of our second matrix, then we're in the 2, 2 location. We're looking at entry 2, 2, which is right here. Second row, second column. And so that's where we put our answer. So it really pays off to be organized when you're doing this. Give yourself enough space. If you know your result is a 2 by 3 matrix, like this example, just make sure you have a large empty space that you're going to be writing your answers in. If you want to, you can even put these blank little boxes in the locations where the numbers are going to go. Okay, so now let's talk about some properties with matrix multiplication. So we have that our matrix A is size n by n, B and C have the sizes for which The indicated sums and products are defined. This is just a general statement saying that we can do these following properties. All right, so the associativity law holds, where we can say B times C first, times that by A. Or we could do A times B first, and then times that by C. The distribution from left and right also holds. So B plus C is the same as, or then times A is the same as A times B plus A times C. And it's very similar with the right distribution. And then we can multiply by a scalar. So we can say A times B, and then times that by R. And that's the same as R times A, that result times B, which is also the same as R times B, and that result times A. And then letter E here is with our identity matrix I. So remember the identity matrix is your square matrix with ones in the diagonal and zeros elsewhere. And so this subscript is letting you know how many rows and columns. So if you left multiply A times your identity matrix, so the number of rows and columns of I matches the number of rows from A. Think of it like almost timesing like by 1. You still get A. And it's the same as if you were to multiply from the right times the identity matrix, but this time it's size n by n because it matches the number of columns from A. It's also just going to give you A. Right, so the left to right order actually matters with multiplication of matrices. And so why I'm going over these properties is because they're not the same necessarily as they are for numbers. So things you know about multiplying numbers, like 2 times 3 is the same as 3 times 2, that doesn't necessarily hold true for matrices. So what I'm saying here is that when you multiply A times B and B times A, they're not always the same. A lot of times they're not the same. And we'll talk about later when they are going to be the same. And so the position of the factors in the product is usually emphasized to make it clear. So when we have A times B, we'll say something like A is right multiplied by B. And if we have B times A, we could say B is right multiplied by A, or in this case, if it's still just A times B, we could say B is left multiplied by A. So it's letting us know the order and how it matters. All right, so here's an example for you. Here's A, matrix A, here's matrix B, and if you multiply them, A times B, here's one result. If you were to change the order, notice this is B times A, and if you were to work out this multiplication, you do not get the same result. Okay, so you want to be careful. Multiplication with matrices is not commutative, so the order does matter. Okay, so if A times B happens to equal B times A, then we say that A and B commute with one another. And so some warnings for us here. In general, these are not the same. A times B is not the same as B times A. And then just be aware, the cancellation laws that you've used with algebra don't hold for matrices, for matrix multiplication. So that means, for example, if you had A times B equals A times C, if these were numbers and variables, you would think, oh, let me just divide by A. That's not true in general with matrices. So A times B equals A times C does not imply that B equals C. And then number 3 here, if a product AB equals 0, so you do your multiplication and you get the 0 matrix, you cannot conclude that either A was 0 or B was 0, like you can in algebra. Normally in algebra we say, oh, if the product of two numbers is 0, one of them had to be 0. Matrices, not true in general. Okay, so next, let's talk about powers of a matrix. We've talked a lot about how to multiply and the properties with matrices. Now let's talk about powers of matrices. So if you see exponent up here, it is a power, and it's just letting you know that you're multiplying your matrix times itself that many times. So if you have A to the third, you have A times A times A. So if A is a non-zero matrix and X is some vector in Rn, then if we said A to the K times X, so we have some powers of A times that vector X, it's the result of left multiplying X by A repeatedly, however many times K happens to be. And then if K happens to be 0, well, think about that. It's the power of 0. You can think of this as like 1, the identity. And so A to the 0 times X just leaves you with X. And so you can think of A to the 0 as the identity matrix I. And then the last thing I want to share with you guys is what's called the transpose of a matrix. And so given M by N matrix A, the transpose of this matrix is going to be an N by M matrix, denoted A transpose. That's how we would read this. And then the columns and the rows basically switch. So here's some examples for you. So look at A here. You have row 1 is AB, row 2 is CD. In A transpose, what was row 1 became column 1. And what was row 2 became column 2. And so you have a new row 1, it's AC, and a new row 2, BD. And so you can look at each of these 3 examples to understand what the transpose is. And now a theorem involving the transpose of a matrix. If A and B denote matrices whose sizes are appropriate for the following sums and products, then these 4 properties are true. A transpose, transpose. So if you transpose the transpose, think of it like undoing itself. The first transpose switches the rows and columns. The second one switches the rows and columns again, and you're back to A. Part B, when you transpose a sum, it's actually really nice. You can actually transpose the individual matrices and then add those up. And you get the same answer. Letter C, if you have a scalar times your matrix and you transpose that, you can transpose your matrix first, switch the rows and columns, and then times it by your scalar, and you'll get the same result. And then last, this one's a little tricky, so make sure you notice the difference. If you have a product, AB, and then you transpose the product, it's the same as if you switch the order and transpose them individually, and then multiply. Okay, so let me make sure you understand this. This is saying product AB, so you multiply that first, you transpose the result. That will give you the same answer if you take B and you transpose it, you take A and you transpose it, and then you multiply. That's what this is saying. And then the transpose of a product of matrices equals the product of their transposes in reverse order. So that's just this one here. Okay, so that's it for our operations on matrices. Thanks for watching.